Okay, hello everyone. Today we have Ratko Darda from Sabancı University, and he's a Marie Curie Fellow. He just started his position a few months ago, and he's going to be talking about Malle's conjecture for finite group schemes. Thank you, Ratko.
Thank you for introduction, and thanks the organizers for inviting me to speak at this seminar, and thanks everyone for coming. So the title of my talk is Malle's conjecture for finite group schemes. Malle's conjecture is a quantitative version of the inverse Galois problem. Recall that the inverse Galois problem asks whether every finite group G is the Galois group of a finite extension of Q. And the Malle conjecture tells you more. It tells you, in a way, how many are there extensions with this Galois group. Here we do this in a new context, the context of finite group schemes. Finite group schemes are sort of generalizations of finite groups, and we'll see how the Malle's conjecture of finite group schemes actually has some application for the standard Malle conjecture. Everything what I say today is based on a joint work with Takiko Yasuda. Okay, so here is our plan. In the first part, I'm going to introduce the question, then I'm going to speak a little bit about finite group schemes, then I'm going to discuss heights, and at the end, I'm going to present a proof of our conjecture for commutative finite group schemes. Okay, let us start with the inverse Galois problem. So you are given a finite group G, and you are asked whether G is the Galois group of a finite extension of Q. This question has been widely studied. It's known in many cases, but still also widely open. And it is known for abelian groups, for Sn, the symmetric group for the n factorial, then the alternating group. Then you have Shafarevich theorem, which solves this for solar groups and some other instances. It's unknown for in general. Concrete group that I could find that it's open is the Mathieu group M23, and there are certain groups PSLN FQ, but I couldn't find a particular N and Q for which this is open because some theories give you solutions for some N and Q, uh, but in general this is open for such groups. Okay, let us now turn to our interest today. The Malle conjecture, as I said, quantifies the inverse Galois problem. It tells you how many extensions are there. Of course, there are infinitely many extensions, but for this reason, we introduce some sort of height or size of an extension. So we let delta be delta k of q be the discriminant of finite extension k of q. And then the conjecture says the following. The number of Galois extensions k over q with the Galois group k over q is the given group G, and the discriminant less than b for b large is having the same asymptotic behavior as the function some constant times b power a log b power b minus 1. A and b are two variants, and since very recently there is a conjecture by Logran and Santens for the leading constant c. Okay, now I'm going to
Excuse me,
generalize a
can I ask a
little.
question?
Yes.
Excuse me. So what is the delta in the notation?
So delta
And
is
G
the
delta B?
discriminant of delta k of q is the discriminant of the extension k of q.
Yeah, but in the notation you have NG delta B.
Okay,
So you want
so
to bound the
here I
delta by
will,
B
in the
and
next slide, I'm going to change delta a little bit. So I'm going to use some other height function, and then, so this makes sense, right?
okay.
So, so delta is sort of height that you use for the problem.
Yes. Okay, thank you.
Okay, so as I said, now I'm going to change a little bit the height function. I'm going to take a transitive embedding of our finite group G into Sn. When I say transitive, it means Sn has a natural action on the set from 1 to n, and we want that the induced action on G is transitive. Then let G rho be a point stabilizer. You take some point in the set from 1 to n, let's say 1, and you look at the stabilizer. If you take some other point, then you get a conjugate subgroup. Now, instead of looking at delta, I look at delta rho, which is the discriminant of the subfield fixed by G rho of our Galois extension K. So now you have like you have the size function delta rho, and again you get the same asymptotic behavior. Now I'm going to define you what are these two invariants. Let let us consider some element G. It is a permutation because G is the capital G is embedded in Sn, and then we define index of G to be n minus the number of orbits of G. So if G is the trivial element, then you have n orbits, and so this index is 0. The A invariant is expected to be the minimum of indices for G not equal to 1. And then you take the inverse. To define the B invariant, let us consider the cyclotomic character. It is going from the absolute Galois group to the, sorry, I should have put a multiplicative group of Z hat. Now we define the action of the absolute Galois group on G, the following one. So we take gamma times G is G power the value of this cyclotomic character. So this makes sense, like, okay. And now we look at this set, G modulo the Galois action and modulo the conjugation. And the resulting elements will be called Q conjugacy classes. And now one can verify that index is invariant for this action. It's also invariant for the conjugation. So the function index descends on this element of the sets that we call Q conjugacy classes. Now B is expected to be the number of Q conjugacy classes with the minimal index, or with the index equal to A minus 1. Let me now say another version of the Malle conjecture that is perhaps found more often in the literature. So you can say it as follows. We will count degree n extensions such that the Galois group of the Galois closure is G and such that the discriminant is less than B. So this is something that like people like to quote as the Malle conjecture. And this is equivalent to the last version that I given. Only the leading constant changes a little bit, because to every like extension here, you can associate some Galois extension with the Galois group G. It is the Galois closure, but this is not quite one-to-one map. So this is why the leading constant changes. Okay, let us look what is known on the Malle conjecture. It has been verified for a billion groups by Wright in 1989. Then we have the work of Davenport Hellbrown. So we can say this thanks to the last slide. Degree 3 extensions with the Galois group of the Galois closure equal to S3. So this has been verified. Then we have the famous work of Bhargava, S4 in S4 and S5 in S5. And the other examples are covered by the very recent advance. So by Alberts, Lemke, Oliver, Wang, and Wood, they show it for so-called concentrated groups, and this covers some other advances like the one by Koymans Pagano for certain L-potent groups. Okay, but again, like there are many groups for which Malle conjecture is not solved. For example, for the alternating group of order 12, we'll see today a lower bound that one can get from like one of our results. And the upper bound also exists, but they are both not quite the ones that are expected. Now, there is another twist in the story. So the conjecture, as stated before, admits counterexamples. So I'm going to give you a concrete group, which is constructed with the cloners, by cloners in 2005. It is the red product of Z over 3 and Z over 2. Recall that the red product is obtained as follows. You take the direct product Z over 3 times Z over 3. You look at this group Z over 2. You act on this direct product Z over 3 times Z over 3 by permuting the coordinates, and you take the semi-direct product. So this is a group of order 18. So it has a degree 6 transitive permutation representation. And what happens is that it has too many extensions. So the actual exponent of logarithm of b is larger than what we expect. We expect b minus 1, where b is the invariant that I have defined. So possible, like we need to change the Malle conjecture. So possible modifications. But the first one that we have is the one by Turkeli in 2007. So Turkeli proposes to increase the exponent b to incorporate these additional extensions that we have. However, from now another very recent result by Wang from the last week, she finds the counterexamples for the Turkeli's version. As far as I understood, certain groups do follow the original prediction by Malle, but Turkeli proposes to increase the exponent b, so it's not correct. And another approach that we are going to deal with today is to remove certain extensions from counting. So we keep the exponent b as it is, but we are not going to count certain extensions for some reasons, and like to have the correct prediction. And let me say a little bit more on the second approach and to some analog. So in Diophantine geometry, we have the following question. It is sort of same philosophy. You count arithmetic objects of a bounded size. So here, the arithmetic objects are rational points, and the size or the heights are the heights that we have. So let X be a smooth fun variety with the risky dense set of rational points. Then we take some line bundle. This is to have the size function or height. And then you get HL to be the height function. This conjecture, due to several people, most notably Manin, Batiev, and Peer, predicts that outside of some thing set Z, the number of rational points of height bounded by B obeys very reminiscent formula as the one in the Malle conjecture. And now let us see what is Z here. So Z can be the set of rational points of a closed subvariety. Namely, it can happen that you have some closed subvariety which accumulates too many points, more points than the rest. For example, if you look at a smooth hypersurface, uh, if you take L is the anticanonical line bundle, then if sum of 27 lines is defined over Q, if you write A and B that you have, you actually get that this line accumulates more than what we expect. So we should remove certain closed subvarieties. And the second thing that can go wrong is that you can have a cover of X, so cover without section. Actually, it's a little bit more general, but I think this is enough to understand. Such that once you do the conjecture for the pullback on yi, again, you get too many extensions. And now you look at the points in the image. Again, so it's too many. And the conjecture cannot be possible for possibly valid for x. So we should remove such points from the count. And now let us try to make some analogs of this for the Malle conjecture, because this is what we're interested into. So if you will try to make the analog of the first one, so you have a finite group G, you would like to look at extensions of some subgroup H, and you look H extensions, and you see whether H extensions contribute to the G extensions. And what happens is that H extensions actually don't produce G extensions, they produce G algebras, which are not fields. And so the first approach doesn't give us anything. And today we are going to see why the second approach gives us something. So we will construct some covers from the set of extensions of a finite group scheme to the set of G extensions, and we'll see that this is the reason why we get too many of them. So this is leads us to the Malle's conjecture for finite group schemes. Okay, now I will start talking about recalling a little bit the theory of finite group schemes or finite schemes. What I will be dealing with is finite étale schemes, finite étale group schemes. Finite group schemes are a little bit more general, and we don't need them for the purpose of this talk. So finite étale Q scheme, we can define it as follows: to be it is a functor in the category of extensions of Q contained, if you want, in a fixed algebraic closure, which is represented by finite étale algebra. So let us see what does happen. So we take finite étale algebra. By definition, this is a finite product of finite extensions of Q. And then we want this functor does spec of A valued at L gives you the homomorphisms from A to L, or in other words, the extensions, the embeddings of extensions, because every homomorphism factorizes through this, of some extension ki to L, and which of course is trivial on Q. Now, finite étale Q group scheme is a finite étale scheme which is a group functor. And the example that the simplest example that we have is we take spectrum product G inside of G of Q, and this has the group structure deduced from G. Such group schemes we call constant group schemes. Then we have the group scheme UN, and this is in the context of the Malle conjecture interesting. So the mu n is a spectrum of Q of t modulo t power n minus 1. This is called nth roots of unity because if you take some extension L, then mu n of L corresponds to nth roots of unity in L. Now, we need some substitute of G extensions for finite group schemes. And we use G torsors, or sometimes they are called G principal bundles. So let G be a finite étale group scheme acting on finite étale scheme X. And you see that X is a G torsor. If you look at the Q bar points, so this is going to be a finite group, this is going to be a finite set, and then this actually makes X of Q bar genuine G of Q bar principal set in the sense of set theory, or in other words, the action is faithful and transitive. We will use notation BG of Q to denote the set of G torsors over Q. And as I said, G torsors will be used as a replacement for G extensions when G is a constant. And now maybe some motivation why this should be used. So if G is constant, and if you have some Galois extension K over Q, then spectrum of K is G torsor. This comes to verify that the Galois action on a set of roots of some generating polynomial is faithful and transitive. And now our second example, what are mu n torsors? Well, they are spectrum Q of t modulo t of power n minus a, where a is some non-zero rational number. Moreover, like in the case of mu n, they admit even like a simpler description than in the case of z over nz. So the BN mu n of Q form a group which is the multiplicative group of Q modulo the nth powers of the multiplicative group of Q. So let me just stress, mu n torsors are not the same thing as Z over nz torsors because these two group schemes are different. They become the same after some finite extension. In general, the three torsors are parameterized by some homology groups. Uh, BG of Q is H1 Q of G, and you can use any homology theory that you like. And you can also use the Galois homology. So then you have the local situation for P prime or for phi infinity, the set BG of QP, is H1 QPG. They are finite, and this follows from some structure results of the local absolute Galois group. Okay, now we would like to define heights on G torsors. The heights in for varieties or the heights such as discriminant are products of local heights. So essentially, it comes to solve the local case. So we take P to be a prime. Now let QP tame and QP unramified be the maximal tame ramified and maximal unramified extension of QP respectively. And then IP tame, let it be the tame inertia group, which is just this. So for all but finitely many map, we are going to construct a map from the G torsors in the local case to some finite set. And let me say what this map is. So first, G torsors over QP. As I said, we can use the Galois homology to compute them. And then for almost all P, the cardinality of G is coprime to P. And we can use, instead of the absolute Galois group, we look at the Galois group of the maximal tame extension of QP. And now the inflation restriction sequence in the Galois homology gives you homomorphism from H1 of this group to H1 of this group. For almost all P, G is unramified at P, and calculating H1 comes to calculate the set of homomorphisms. And because now G is not necessarily commutative, we also need to mod out by conjugation. By using the structure of IP tame, like
Excuse me, can I
this.
ask a question?
Yes, sir.
Are you assuming anything on the order of G?
I
Any,
said,
do you have any
so
assumptions?
yeah. So here, so this we use P prime, and this we do for all but finitely many exceptions. So for all P which are coprime to the cardinality of G.
Okay, exactly. Thank you.
Yeah. Okay. And once, okay, so this is some like union of cyclic groups. And so this homomorphism factorizes through actually some finite cyclic group to G of Q bar. And one can take E to be the exponent of G or the least common multiplier of the orders of elements in G. And then at the last step, what I do is I define some finite étale scheme such that its Q bar points are this. So this scheme is going to be pointed scheme, meaning that you have some preferred element. It's the class of the trivial homomorphism. So to summarize what we have done on this slide, we construct a map from H1 QPG to some finite set G minus 1 equibar. So this map in the literature for G commutative uh, has been studied, but I haven't found it anywhere for G non-commutative. Okay,
Excuse me, can I ask a question? So this
sure.
G minus one, so do you construct this globally or?
Yes, yes. This is globally constructed. This is because so this description is somehow uh, so sorry. This thing is something that does not depend on the prime.
And so is G minus one also a child of a scheme?
Yes, it is a Taylor group scheme. Yes.
Does it have a
So
name?
if G, sorry.
Does it have a name?
So it
Like a
has a
twist
name
or
when G is
something?
commutative. It's called Tate minus one twist.
Okay. Okay.
But like I have seen this only for G commutative, and yeah, you can repeat the
Yeah.
construction for G non-commutative. Okay. Okay, we have a map from the set of G torsors over QP to some finite pointed set. Now let us see a little bit examples of this G minus one Q bar. What this thing is. If G is constant, then G minus one of Q bar modulo the Galois action gives you the Q conjugacy classes of G, that the thing that we have seen in the beginning. And if G is mu n, then mu n minus one is the constant group Z over NZ. Okay, so why we were doing this? We want to define the local heights. And now once you have this residue map, you can take uh, like not quite any function, but you can take some functions here and just pull back to get, okay, we need also to add the p power if you want to make exponential heights. But essentially we need functions here. So we say that the counting function is a gamma q invariant function on the set of q bar points of G minus one to R at least zero, such that this uh, neutral element maps to zero. Examples, if G is a transitive permutation subgroup of Sn, then the index that we have seen is an example of a counting. And for any a finite étale group scheme G, one has that the discriminant exponent is an example of counting function. So one can verify this. Okay, now to define heights, as I said, now what we do to an element x, we associate p power, the counting function evaluated at the value of the residue map at x. So this is this works for almost all primes p. For finitely many exceptions, you take hp to be any function. So these sets are finite. Okay, now to define a global height, uh, we let IP to be the canonical map from G torsors to the G torsors over QP, and then height is defined to be product of HP IP of X overall P prime or P infinity. So this product is a finite product because one can verify that the image of X or a fixed X under this map composed with the residue map goes to the trivial map for almost all P. And the choice that I have made it here will at the end make different height function, but the quotients of the two height functions is bounded because the sets PG of QP are finite. Now, for any height function, we have that we have what I call like one calls for varieties Norco property. So we have Norco property here. The set of G torsors of bounded height is finite for any b bigger than zero. This follows by the Hermite-Minkowski theorem for discriminant, and then like any counting function can be sum of its multiples is going to be bigger than the discriminant counting function. And then how to define A and B invariant? Well, do the same as in the case of index. So A is the minimum of the counting function for non-neutral elements, power minus 1, and B is the number of orbits with counting function minimal. And now for finite group schemes, hence it's quite natural to try to guess that the number of G torzos of bounded height is respecting this behavior. But of course, this cannot be true because of the Kluner's counterexample. And let us see what is going on. So one can have, so far I used BG and BH as notation, but in fact, they have some algebra geometric structure, namely they are some Delhi-Mumford stacks. So you can have a finite cover of stacks, and you can pull back your counting functions. So you have a counting function here, and you can evaluate A and B invariants, and it can happen that A and B invariants of the pullback are bigger than the original ones. And then if you look at the points of coming from H torsors, there are already too many of them. And this H, we will give an example of this in a bit. Even G is constant, even G is a genuine group, H can be a non-constant, so it can be some finite group scheme. So this is motivated by the work of Lehmann, Segbuta, Tanimoto for varieties. And let me give you the case of the Kluner's example. So G is the red product Z over 3 and Z over 2. R is the normal subgroup of index 2. Then you take any extension, any G extension K. This is a degree 2 extension of Q, the subfield fixed by R. Then we twist R and G by the images sigma and sigma tilde of of the so sigma and sigma tilde are the images of spec KR inside of here and here respectively. So the first one is going to be some, so sigma is going to be some out R extension, and sigma tilde is some out G extension, and somehow they are compatible. So you can twist R by sigma, you can twist G by sigma tilde, and you are going to have a map. And you always have a canonical map here because sigma tilde is twisting by sigma tilde is here is some inner twist. So this is a example of Kluner's. So now you need to, of course, to evaluate the A and B invariants and to see that they increase. But this is quite straightforward. So what we predict is that the number of G torsors outside of Z, where Z is the union of all these morphisms where A and B invariants increase, should be this. And this is what we conjecture. And now I'm going to discuss in the rest of talk the case when G is a commutative finite Italo group scheme where we can prove our claim. So in the case when G is commutative finite Italo group scheme, BG of Q and BG of QP have structure of abelian groups. Moreover, H1QPG or BG of QP are finite groups. So what do? We define the adelic space of BG to be the restricted product over all primes of BG of QP with respect to subgroups BG of ZP. So BG of ZP. So of course you need to take a model of G over the ring of integers, and then like taking any two models will give you this isomorph the same space actually the same. Okay, so you get a locally compact group, and it has a Haar measure. So this like eventually will lead you to use some Fourier analysis. Now we use a result due to which can be deduced from the Poitou-Tate exact sequence. It says that the image of BG of Q for the diagonal map, BG of Q to BG of Q, is discrete, closed, and co-compact. So it has a so the difference like so this we know also from Tate's thesis, like there G is GM. The only difference that we have is that the map I is not injective. The map I here has some kernel, which is the Tate-Farovich group of G, which is a finite group. Right? Okay. Now we can also now, as I said, we are going to use Fourier analysis. We can study the Pontryagin dual of BG of AQ, and moreover, we don't study the whole dual, we study the automorphic characters, and they are identified with GD torsors, where GD is the Cartier dual of G. Then another useful property that we use is that local heights. So uh, uh, we have height HP on this set BG of QP, but you can also define the global heights BG of AQ. So the local heights are invariant for this uh, uh, group BG of ZP because this group is in the kernel of the ResD map, which can be easily seen. Okay. Now, what is our method? So we adapt like to our context the proof of Batyrov and Schinkel of for the number of rational points of bounded height on toric varieties. So there you also have harmonic analysis because toric variety has a torus. You embed rational points of torus to adelic points. So this is what we're doing. So we define z of s to be the height zeta function, which is sum of heights power minus s, where s is some complex number sufficiently big so that this converges. So z of s becomes some holomorphic function on a part of complex plane, and eventually we would like to extend it as much as possible and to use Tauberian results to deduce the counting behavior. As I said, the map I is not injective. You have a Tate-Shafarevich group, which is a fine group in this setting. So we now sum over X in the image of. So this is some, as we have seen on the last slide, this is some discrete, closed, and compact subgroup of BG of adelic points. In the last step, we use the Poisson formula. Like the Poisson formula says, okay, integrating this function on a subgroup comes to integrate the Fourier transforms on some dual space. So here you need to integrate it over, you need to sum it, the measure is going to be a discrete one, over the automorphic characters, and we have identified the automorphic characters with the GD torsors, with the torsors of the Cartier dual of G. So this notation that I have used is the Fourier transform of the function h minus s with respect to the character chi. So now the last sum reduces to fine sum. This is the property that I said. You have that your height, your local height is invariant for PG of ZP. The global height is going to be invariant for some large compact subgroup. And the like if you do the quotient, it's going to be going to reduce to a fine sum. And now we need to analyze these terms, these Fourier transforms. Uh, and if you write down them, you will see that they are in a way close to certain L functions. So to chi, we associate certain Galar representations, and H hat is going to be the L function of the representation attached to chi times some holomorphic function. So essentially, you are left to analyze the L functions, but this is well known. So we can deduce what is the pool, what is the uh, order of the pool of the function z, and hence by Tauberian results, we can deduce the asymptotic behavior for the number of G torzos of bounded height. So this generalizes several results in the literature. Um, the result of Wright for the counts of abelian extensions, but also some results of Wood. So this is the theorem that I described. Uh, so the asymptotic value is this one. Here you don't have this problem with the thin sets. You don't need to remove anything. The constant C is like product of several factors. Uh, there are some factors which are related to the arithmetics of this stock PG. And there is one factor which is volume. And let me say something more about this. So what we do, we define a measure omega on the direct product, so product over all primes P of the sets BG of QP of the groups BG of QP. So this is different from the restricted product we have. So this set is larger. We define measure omega on this set, and so we look at open subsets of this set. So let me give you an example. So you can take subsets of BG of QP, whatever you like, at finitely many places, and for others you take everything. But there are some others. And you want that the boundary is negligible. For subset I said, the boundary is already negligible. And now you count, you would like to count torsos lying in this subset U. Actually, it's not quite lying inside because the map I is not injective, but you would like to count torsors such that the image under the map I lies in the set of U, and you would like to see what proportion of them lies inside. So what we prove is that at the limit, like if you do these proportions, you will converge to the volume of U. So like we can see that G torsos are equidistributed in this uh, uh, in this space. And if you want to have a practical application of this, what does it mean? It means that finitely many, or not just this, but let's say at finitely many places, you fix your local conditions on G torsors, and you count using this theorem how many torsos of bounded height are there. Okay, and let me say in the last 3 minutes some more results. So this slide counts all G-torsors. Like you may want to count connected G-torsors, which is a little bit different story. Like it's harder. In my PhD thesis, I've proven the counts, the precise asymptotic behavior for the number of connected torsors when G is mu n. Uh, but okay, and then second result. So using uh, Devisage, and the result from uh, this slide, we can obtain a lower bound for the number of connected G torsos for G semicommutative. So by G semicommutative, I mean that this group can be obtained from finite commutative Étale group schemes by using semi-direct products and quotients by normal subgroups. And for example, you can get bound that is first obtained by Alberts, but like we also get this bound, which is currently the best bound for the number of A4 extensions. It's of bounded uh, height with respect to the uh, like representation A4 embedded in S4, which is B1 over 2. And let me just say, so it is Harari who proved that G semicommutative always admits one connected G torsor. So he solves the inverse Galois problem. And here we get a quantitative bound, and we use very different methods. So I would like to stop here. Thank you.
Thank you, Ratko. So, any questions or comments? So, when G is non-abelian, non-commutative, let me say, are there results in that direction?
So for non-abelian groups, you have some of the results that I listed, like S3, S4, S5, and concentrated groups. But when it comes to group schemes, there is one like a result that you can deduce, but it's not quite new. You can take some constant group for which the counts are known, such as let's say S3, and you can do some inner twist, and there is a canonical bijection between torsors. The heights behave more or less the same way, so you can deduce the counts, which is not quite a new example, but so I don't know. I don't think there are some other results for genome constant. So in this uh, theorem here, we get for this commutative some bound. This A does not need to be optimal, but if your height is related with the semi-commutative structure, then it is. Like when I say optimal, I mean the one predicted by the Malle conjecture. Yeah. But besides this, I don't think there are some other results.
Yeah. Any more questions or comments? So let's take Ratko once more. Let's think. Uh, and I hope we will meet in person at some point since you are in Istanbul.